to a rather stimulating intellectual foray into the fascinating world of cognitive ergonomics. We're embarking on a deep dive today
Indeed.
to explore the intriguing evolution of our understanding of human-machine interaction.
Yes, a journey through time, tracing the genesis of safer and more efficient systems.
It promises to be a captivating exploration. Now, to set the stage, perhaps you could elaborate on the prevailing philosophy in the early days of system design, the concept of separation of functions.
Ah, yes, the separation of functions, a rather axiomatic belief in those nascent stages of technological development. It was a simple, perhaps even simplistic view of the world, a neat dichotomy.
Between human agency and mechanical operation.
Precisely. The assumption was, you see, that by relegating human involvement to an absolute minimum, one could invariably achieve optimal outcomes.
A rather bold assumption, wouldn't you say?
Perhaps in retrospect, it's quite fascinating, actually, how this philosophy inadvertently mirrors the etymology of the term astronaut.
Astronaut, meaning star traveler, if I'm not mistaken.
Precisely. It inadvertently underscores the perception of humans as passive voyagers rather than active orchestrators in their celestial endeavors.
Fascinating indeed. But tell me, this notion of intentionally sedating astronauts to mitigate potential human error, a rather unorthodox proposition, wouldn't you say? Could you shed some light on the rationale behind such a concept?
Certainly, it stemmed from a rather pervasive trepidation, a fear, if you will, regarding the inherent fallibility of human actions, particularly within the context of those intricate and perilous spacefaring endeavors.
A fear of the human factor, as it were.
Precisely. The prevailing sentiment was that attenuating or perhaps even eliminating conscious human interaction with that labyrinthine machinery would, in effect, mitigate the risks attendant upon human intervention.
A rather drastic approach, to be sure.
Yeah.
And one that, as history would soon demonstrate, was predicated on a fundamental misapprehension of the symbiotic relationship between human cognition and technological operation.
Indeed.
Our sources point to three compelling case studies, each a poignant testament to the limitations of this rigid separation of functions dogma.
Ah, yes. The cautionary tales of Apollo 13, the Tenerife airport disaster, and the 3 Mile Island incident.
Each a stark reminder of the inherent complexities of human-machine interaction and the perils of underestimating the human factor in system design.
Shall we delve into these historical vignettes then?
Let's start with Apollo 13, an episode indelibly etched into the collective memory of humankind's ventures beyond the terrestrial confines. Could you perhaps delineate the key junctures in that fateful chain of events?
The events leading to the oxygen tank explosion.
Precisely.
It was a veritable concatenation of seemingly innocuous oversights, you see, a cascade of failures culminating in a near-catastrophic denouement.
And the genesis of this chain of events.
It can be traced back to a seemingly inconsequential design modification undertaken in 1965.
A modification, if memory serves, necessitated by the need to ensure dual voltage compatibility across the spacecraft's electrical systems.
Precisely. However, a critical detail appears to have been lost in the labyrinthine channels of communication, a rather unfortunate oversight.
Resulting in
One component supplier remaining oblivious to this revised specification. A seemingly trifling oversight, to be sure, yet one that would have momentous consequences. It set the stage, you see, for a series of unfortunate events that would ultimately threaten the very survival of the Apollo 13 mission.
a cascade of failures commencing rather inauspiciously with a seemingly trivial mishap involving an oxygen tank.
Ah, yes, the dropped oxygen tank.
A drop of a mere 5 centimeters, if I recall correctly.
Precisely. Yet this seemingly insignificant tumble resulted in undetected damage, a latent flaw lying dormant within the vessel's critical life support system. It was, in essence, a ticking time bomb awaiting the opportune moment to manifest its pernicious potential.
And this latent flaw would, as fate would have it, play a pivotal role in the unfolding drama.
Indeed. It was during a routine pre-launch inspection that the next link in this fateful chain emerged.
The inability to fully evacuate the aforementioned oxygen tank, a direct consequence of that terrestrial tumble,
Precisely. A perplexing conundrum, to be sure.
leading to the adoption of a rather unorthodox expedient.
The activation of the tank's internal heaters.
In a valiant attempt to vaporize the recalcitrant liquid oxygen and facilitate its expulsion.
An ingenious solution, perhaps, yet one fraught with unforeseen peril. For unbeknownst to the ground crew, a critical safeguard against excessive thermal escalation had fallen victim to that insidious voltage incompatibility.
The thermostat.
Precisely. When subjected to an incongruous electrical potential, it simply ceased to function, rendering the oxygen tank vulnerable to a perilous thermal surge.
A most unfortunate oversight, to be sure.
Indeed. This failure, coupled with the activation of the tank's heaters, resulted in an alarming escalation of temperature within the oxygen tank.
Reaching, if I recall correctly, a scorching 500 degrees Celsius.
Precisely. An inferno within the very heart of the spacecraft's life support system. This thermal onslaught wreaked havoc upon the insulation, shielding the tank's delicate electric wiring.
Effectively transforming it into a potential incendiary device.
Precisely. And so it was that Apollo 13, a testament to human ingenuity and ambition, unknowingly carried within its metallic bowels a ticking time bomb, a latent failure poised to transmute a routine lunar mission into a desperate struggle for survival. A latent menace indeed, lurking within the very heart of the spacecraft's life support system, and the catalyst for this dormant threat to erupt into a full-blown crisis. A rather ironic twist of fate, wouldn't you say?
Ironic in what sense?
It was, you see, a routine operational procedure, an action intended to ensure the smooth functioning of the spacecraft's systems.
I'm intrigued. Do tell.
On that fateful evening of April 13th, 1970, as Apollo 13 hurtled through the celestial void towards its lunar rendezvous, Mission Control issued a seemingly innocuous request.
A request for?
The activation of the oxygen tank fans, a standard operation intended to maintain accurate pressure readings.
And this seemingly mundane action?
It proved to be the proverbial straw that broke the camel's back, triggering a cascade of failures that would test the very limits of human ingenuity and resilience.
The activation of the damaged tank's fan, in the presence of a highly oxygenated environment, created a perfect storm for disaster.
Indeed. A stray spark ignited the compromised wiring, triggering a conflagration within the oxygen tank,
Resulting in
a catastrophic explosion that reverberated throughout the spacecraft.
an explosion that not only shook the physical structure of the spacecraft, but also shattered the prevailing paradigm of separation of functions.
A poignant testament to the intricate interconnectedness of human actions and technological systems.
Exposing the inherent limitations of such a rigid approach to system design.
Indeed, Apollo 13, for all its harrowing drama, ultimately highlighted the indispensable role of human adaptability and resilience in the face of unforeseen adversity.
It was the crew's ingenuity and resourcefulness, coupled with the unwavering support of Mission Control, that transformed this potential catastrophe into what has been hailed as NASA's most successful failure.
A compelling testament to the indomitable spirit of human innovation.
And a potent reminder that human ingenuity, rather than being a liability, can serve as a vital asset in navigating the complexities of human-machine interaction. However, before we delve further into the conceptual implications of this extraordinary feat of human resilience, let us turn our attention to another sobering example of the perils inherent in the separation of functions dogma,
You're referring to?
the Tenerife airport disaster. This tragedy, unfolding not in the boundless expanse of space, but amidst the bustling terrestrial realm of air travel, offers equally profound insights into the intricacies of human-machine interaction, particularly under conditions of duress.
An excellent suggestion. The Tenerife airport disaster, while seemingly unrelated to the realm of space exploration, provides a valuable counterpoint to the Apollo 13 saga. It underscores the universality of the principles underlying human-machine interaction, regardless of the specific technological domain.
This tragic confluence of circumstances unfolding on a fog-shrouded runway culminated in the deadliest aviation accident in history.
A stark reminder that even the most meticulously engineered systems, operated by highly trained professionals, can succumb to the cascading effects of unforeseen events and human fallibility.
The stage for this calamity was set by a series of events that conspired to create an atmosphere of heightened tension and operational complexity.
A bomb threat, a diverted flight path, and a runway shrouded in dense fog, all contributing to a precarious situation ripe for miscommunication and misjudgment.
And amidst this maelstrom of external pressures, the human element, with all its inherent complexities and vulnerabilities, would play a pivotal role in the unfolding drama.
Tragically so. Miscommunication between the KLM and Pan Am crews, coupled with ambiguous clearances from the air traffic control tower, created a cascade of misunderstandings and misinterpretations.
Leading to
A fatal misalignment of perceptions and actions. The KLM flight, believing it had received unequivocal takeoff clearance, initiated its takeoff roll.
Wow.
The Pan Am flight, delayed in exiting the runway due to the obscured visibility, remained directly in its path.
A fatal misalignment indeed. The KLM flight, accelerating through the dense fog, collided with the Pan Am aircraft, resulting in the loss of all 587 souls on board both planes.
Paris stands as a chilling monument to the inherent fragility of complex systems.
A stark reminder that human cognitive limitations, exacerbated by external pressures and environmental factors, can have devastating consequences, even within highly regulated and technologically advanced domains such as aviation.
Indeed. However, before we succumb to an overwhelming sense of pessimism, perhaps we should turn our attention to a conceptual framework that offers a way to visualize how these seemingly minor failures can align to cause catastrophic accidents.
You're referring to James Reason's Swiss cheese model.
Precisely, a metaphor that has proven invaluable in understanding the genesis of accidents.
Could you elaborate on this model and its relevance to the incidents we have discussed?
Of course, the Swiss cheese model, a visualization of accident causation, posits that safety systems are akin to slices of Swiss cheese.
Each with its inherent holes representing weaknesses or vulnerabilities.
Precisely. These holes can arise from latent failures, such as design flaws or organizational deficiencies, as well as active failures, typically represented by human errors or equipment malfunctions.
And the crux of this model, as I understand it, lies in the alignment of these holes, creating a trajectory for disaster.
Exactly. In isolation, these individual weaknesses may pose little threat, but when they align, creating an unobstructed path through multiple layers of defense, catastrophic events can occur.
The Tenerife airport disaster, viewed through the lens of this model, reveals a chilling alignment of latent and active failures.
Indeed. The bomb threat, the diverted flights, the dense fog all contributed to creating a situation ripe for miscommunication and misjudgment.
And within this context of heightened vulnerability, the ambiguous clearances from the air traffic control tower, coupled with the KLM crew's misinterpretation of their takeoff instructions, formed the final links in a tragic chain of events.
Each hole in the metaphorical Swiss cheese, representing a point of failure, contributed to the ultimate outcome. The Swiss cheese model, in essence, provides a framework for understanding how seemingly disparate factors can coalesce into a critical incident. It compels us to look beyond individual errors and consider the systemic vulnerabilities that underpin such tragedies.
A powerful tool for comprehending the complex interplay of factors that contribute to accidents, to be sure. And perhaps more importantly, a framework for designing more resilient systems by anticipating and mitigating these potential points of failure.
Indeed. The Swiss cheese model, while acknowledging the inevitability of human error, also underscores the importance of constructing robust systems with multiple layers of defense. It emphasizes the need for clear communication protocols, comprehensive training programs, and a culture that encourages the identification and reporting of potential hazards.
A proactive approach to safety, one that recognizes the interconnectedness of human actions, technical systems, and organizational factors.
Precisely. But before we delve further into these contemporary implications, perhaps we should first examine the 3 Mile Island incident.
The final case study in our historical exploration.
An incident that sent shockwaves through the nuclear industry, raising profound questions about the safety and reliability of complex technological systems.
The incident, if I recall correctly, was precipitated by a seemingly mundane malfunction, a failure in the plant's secondary cooling system pump.
A failure that, in a well-designed system, should have been readily contained. However, a confluence of latent failures conspired to transform this routine malfunction into a major crisis.
Backup pumps, intended to compensate for such failures, remained inactive due to closed valves, a legacy of recent maintenance work.
A classic example of a latent failure lying dormant within the system,
waiting for the opportune moment to wreak havoc.
And to further complicate matters, a pressure relief valve, designed to alleviate excess pressure within the reactor, malfunction, becoming stuck open.
But wasn't there an indicator light to signal this critical failure?
There was. However, and this is where things took a decidedly unfortunate turn, the indicator light provided misleading information,
suggesting
that the valve was closed when in reality it remained stubbornly open.
A dangerous disconnect between the actual state of the system and the information available to the operators.
A situation ripe for misinterpretation and misguided actions. And tragically, that is precisely what transpired.
The operators, confronted with a barrage of alarms and confusing instrument readings, struggled to comprehend the unfolding situation.
Their training, heavily reliant on a separation of functions paradigm, proved inadequate for diagnosing such a complex, interconnected failure,
leading them to make a fateful decision.
They disabled the emergency cooling pumps, believing based on the misleading information available that the reactor was already overfilled with coolant.
A decision made with the best of intentions.
But one that inadvertently exacerbated the situation, depriving the reactor core of vital coolant.
Ultimately leading to a partial meltdown.
3 Mile Island, for all its technical complexity, ultimately underscores a fundamental truth. The human element, with all its inherent strengths and weaknesses, remains an integral part of any complex system. It compels us to move beyond the simplistic notion of separation of functions and embrace a paradigm where human cognitive capabilities are understood, supported, and integrated into system design.
A paradigm shift that recognizes the inextricable link between human actions and technical systems.
Emphasizing the need for designs that support human cognition and decision-making, especially in handling unforeseen circumstances. Now, having examined these historical case studies, let us transition to the evolution of cognitive ergonomics as a discipline.
It's quite a journey, from attempting to erase the human element to recognizing its critical role. How did this shift in thinking, this emergence of cognitive ergonomics as a distinct discipline, come about?
Well, it can be traced back to a period of intense intellectual ferment. A series of gatherings brought together luminaries from seemingly disparate fields.
A convergence of minds, united by a common goal.
Indeed, to forge a new understanding of human-machine interaction, one that acknowledged the primacy of human cognition.
In shaping the design and operation of complex systems.
Precisely. Among these seminal events, the NATO Advanced Study Institutes stand out. Their very titles reflect the evolving trajectory of thought in this area.
From separation of functions to mental workload to intelligent decision support systems.
A veritable intellectual odyssey, mirroring the trajectory of our own exploration today.
It's fascinating how the language itself evolved alongside our understanding.
Indeed. A particularly significant milestone emerged. The 1986 NATO ASI, held in San Miniato, Italy.
An apt location for a gathering that sought to bridge the chasm between the human mind and the burgeoning realm of intelligent machines.
Quite right. The San Miniato gathering was a veritable who's who of cognitive ergonomics pioneers. It fostered a sense of shared purpose.
A gathering graced by such luminaries as Jens Rasmussen, Neville Murray, Eric Honegal, Jim Reason, David Woods, Don Norman, and William Wegener.
To name but a few. And amidst this assembly of brilliant minds, a serendipitous encounter occurred, one that would have profound implications. The attendees were treated to a demonstration of the Xerox Star.
Ah, yes. A groundbreaking computer system.
It incorporated a revolutionary graphical user interface, a laser printer, Ethernet connectivity, and the object-oriented programming language Smalltalk.
A confluence of technological innovations.
Which would soon revolutionize the very way humans interacted with computers.
It's remarkable to consider how a system designed for a specific purpose could have such a profound and unanticipated impact.
Indeed. A testament to the unpredictable nature of innovation.
And the interconnectedness of seemingly disparate fields of inquiry.
It was through the lens of this revolutionary system that the attendees at San Miniato glimpsed a future where computers could become tools for augmenting human intellect.
Rather than intimidating behemoth.
Precisely. The San Miniato gathering marked a turning point. It solidified the field's foundations.
Setting the stage for its rapid growth and expanding influence.
And as we stand today, amidst a technological landscape transformed by the very innovations foreshadowed at San Miniato, the principles of cognitive ergonomics remain as relevant as ever.
It's a testament to the enduring power of these ideas.
And their ability to guide us in navigating the complexities of our increasingly technological world.
For in the end, the true measure of technological progress lies not in the sophistication of our machines, but in their ability to empower human beings.
To extend our reach, enhance our capabilities, and ultimately enrich our lives.
A sentiment that echoes the very essence of the term astronaut, star traveler, a symbol of human ambition, ingenuity, and the relentless pursuit of knowledge. As we conclude this deep dive into the origins and evolution of cognitive ergonomics, we are left with a profound appreciation for the intricate dance between human cognition and technological innovation.
From an early attempts to separate these domains to the contemporary embrace of their symbiotic relationship.
Our journey has revealed the profound implications of understanding and supporting human cognitive capabilities
in the design and operation of complex systems.
And as we venture forth into an increasingly automated future, The lessons gleaned from these historical incidents and the insights offered by the pioneers of cognitive ergonomics will serve as invaluable guideposts.
By embracing a human-centered approach to technological development, we can create a future where technology empowers rather than endangers.
A future where human ingenuity and machine intelligence converge to create a world of unprecedented possibility and progress.
A future where, like those intrepid astronauts who first ventured beyond our terrestrial sphere, we navigate the complexities of the technological landscape with wisdom, foresight, and an unwavering commitment to the well-being of humanity.